All right, in this podcast, we're going to talk about how we identify a buffer system. Okay, so first off, let's just reiterate, buffers are very useful because they are going to resist a change in pH. So they're super important in biological systems such as our blood. They can help us understand biochemical applications, and they can also be used in industry for products to help stabilize the pH of a product. All right, so remember again that buffer regions, we find buffer regions when we're titrating a weak acid with a strong base. And so in this region, basically what we have is we have some undissociated, didn't mean to move the page. We've got some undissociated conjugate base, undissociated acid. We've got some conjugate base. We've got our spectator ions of the salt, and then, of course, water. The Na is a spectator ion, as I mentioned, that is produced as part of the salt product, and it's not going to affect our equilibrium. So basically, the two species that we're looking at that comprise the buffer are the acid and the conjugate base. Okay. So let's look at what makes a buffer resist pH. So we're going to look at that previous graph. We're going to look at that, but we're going to focus in on half equivalence. And we know that at half equivalence, the amount of acid and conjugate base are equivalent. So here you see I've kind of set us up a little calculation. Basically, we've got our 25 mils of our acid and then 12.5 mils of the NaOH, which is the volume for half equivalence at this point. We see that the NaOH is the limiting reactant, so it basically goes away. And then our remaining amounts of acid and conjugate base are equivalent. All right, so if we think about that system where we have the 1.25 times 10 to the negative third moles, what would happen if we were to add additional base to that system? So if we were to throw some OH minus into that system, what's going to react with it? Well, hopefully you're sitting here thinking, well, the acid, right? So the acid is definitely going to react with our additional base, and it's going to give us water and then more of our conjugate base. So this would be the okay, baby. This would be the written expression for the reaction. All right, now in converse, if we were to add acid to this solution, a strong acid, so it's giving us all H pluses, then our conjugate base would be grabbing a hold of that H plus and producing more of the bound weak acid. Okay, so there's the reaction for that. So hopefully what you're seeing is that whether we're adding acid or base, it's basically just their opposing processes. So no matter if we're adding OH minus or H plus, when you have a buffer system, there's always a species available to counteract it. Again, remember the relationship between our two species, they're conjugate pairs. All right, so again, another way to look at it. So for a weak acid, we've got lots of undissociated acid. And our salt, we've got lots of conjugate base. So we have plenty of acid to react with the bases and plenty of bases to react with any acids we add. So basically what you need for a buffer is you need an acid-salt pair. So for example, if I had my weak acid HF, I need anything that has that conjugate base part, that F. So like KF is a good example because K is always soluble. So it's just going to give us our little S minus, F minus floating around. All right, and then like for formic acid here, rip off one of the H's and you get HCOO minus. And then if you put a K on that, that's our salt. So you just got to make sure that you always end up with the weak acid and the conjugate base form of that in a salt. All right, so if we were to look here, which one of these would make a buffer solution? Okay, so we've got our weak acid, strong acid. So that is definitely not weak acid conjugate base. Okay, then we have strong base, weak base. Okay, again, not a conjugate pair. All right, and then we've got weak acid and salt that has the conjugate base in it. There's your buffer. And then the bottom one is just strong acid, strong base. So there's your neutralization. So you definitely need your weak acid, and then that NO2 minus, that's your conjugate base of your weak acid. All right, so I had a little typo on this one, so I kind of corrected it. All right, so can we form a buffer with a strong acid and a weak base? So we've been talking all about weak acids, and if we reacted them with a strong base, what we basically end up for our buffer is the weak acid and the conjugate base. There's your buffer part of that, okay? These are only going to give us pHs, though, below 7. So at least in the buffer region. So what about if we wanted a basic buffer? Can you have a strong acid with a weak base? So if you take a weak base and you react it with a strong acid, you will get another buffer situation. This time, though, we've got the weak base and the conjugate of the weak base, which would be the conjugate acid. So it's like a HB kind of deal, okay? So these are going to give us a basic buffer region, okay? So it's going to be above 7. All right, and here's some examples of some weak bases and their salts. So NH3 is a weak base. If you add an H to it, NH4 plus, that is the conjugate acid of it. Okay, again, methylamine. Okay, there is our weak base. Remember, bases accept H's. So if we gained another H here, then that would be our conjugate acid. Okay, so, all right. Okay, here's one. So ethylamine. This one, oh, I just noticed this formula is actually wrong. It should have a little 3 there. Okay. All right, so ethylamine, there's your weak base. It grabs another H. There's the other H it grabs. So there is your conjugate acid.